Reality is not a straight line but a tangled web of time. The light from a long-dead star can whisper secrets of tomorrow, and this is the frontier where chronotunnels and stellar echoes dance. We are about to explore what happens when time and space violently collide. By the end of this, you will understand how these cosmic phenomena could rewrite the fundamental laws of physics. We will investigate if the past is truly set in stone and what strange messages might be echoing across the ages from forgotten stars. What does it truly mean for the future to already be written in the light of the past? A chronotunnel is a theoretical conduit where time and space are no longer separate. Think of the universe not as a static stage, but as a dynamic, flowing river. A wormhole is often described as a bridge across a vast spatial distance, folding the river onto itself. A chronotunnel takes this a step further, suggesting the bridge could also connect the river's upstream past to its downstream future. This is not mere science fiction. The brilliant physicist John Wheeler theorized a turbulent quantum landscape he called spacetime foam. In this foaming sea, at the very smallest scales, countless tiny tunnels and bridges might be constantly bubbling into existence and vanishing again, all around us. These fleeting structures hint that the rigid flow of time we experience could be an illusion, a surface effect of a much deeper and more chaotic reality. For a chronotunnel to become stable, to become something more than a quantum flicker, it would require forces of almost unimaginable power. The intense gravity near a black hole, where space is warped and time is stretched thin, is one of the few places where the fabric of reality might be persuaded to form such a permanent passage. Grasping this concept means wrestling with the giants of physics, general relativity, and quantum mechanics, and accepting a profound possibility. Time may not be a one-way street, but a fluid dimension we could, in theory, navigate. If that is true, then the past might not be a locked room. It could be a place we can visit, or one that can reach out to us. And what if something from a distant age is already trying to send a message, not through a man-made device, but etched into the very light of the stars themselves? That faint, repeated signal from a distant quasar is more than a cosmic curiosity. It is a stellar echo. Picture a shout across a vast canyon where the sound bounces off different rock faces, returning to your ears at slightly different times. Now scale that up to the universe itself. A stellar echo occurs when light, or even the ripples of gravity from a colossal event like a supernova, is delayed, bent, or duplicated on its journey across space. This creates a ghostly afterimage, a replay of a moment from the distant past. The mechanism behind this is often gravitational lensing, where a massive object like a galaxy cluster warps the fabric of spacetime around it. This warping acts as a natural telescope, magnifying the light from objects behind it, and sometimes splitting that light into multiple paths. Each path is a different road through the cosmos, and each one takes a slightly different amount of time to reach us. So we might see the same star explode not once, but twice or even multiple times in our sky, each apparition showing us the event at a different stage. These are not mere illusions, they are real streams of data carrying encrypted information about the universe's history, its composition, and the very nature of reality. By studying stellar echoes, we effectively operate a celestial time machine. We can observe a single cataclysmic event from several temporal perspectives, giving us a unique test for our models of the cosmos. We can measure the expansion of the universe with greater precision, and even probe the distribution of the mysterious dark matter that shapes these cosmic lenses. But this incredible tool leads to a deeper, more unsettling question. What happens when these echoes, these literal pieces of the past, do not just travel through space, but begin to interact with its most fragile and twisted structures? What occurs when a stellar echo meets a chronotunnel? The mathematics describing this cosmic dance are written in the language of gravity itself. Einstein's field equations reveal that when time and space collide, it is not a destructive impact but a profound unification. Mass and energy dictate the very shape of reality, curving the fabric of spacetime around them. Picture a still pond. Now, drop two stones into the water some distance apart. The gentle ripples from each stone expand outward, and when they finally meet, they do not crash. They merge, they interfere, creating intricate new patterns on the surface. This is the essence of cosmic interaction, but on a scale of almost unimaginable power. When the objects involved are neutron stars or black holes, the curvature they create is so severe that time itself is stretched and warped. Light no longer travels in straight lines but follows these deep curves, and matter is pulled along for the ride. Our current understanding of physics suggests that at the very smallest scales, the fabric of reality might not be smooth and continuous. Theories like loop quantum gravity propose that spacetime itself could be woven from discrete, tiny loops. A collision between time and space, in this view, might be a fundamental reconfiguration of these building blocks, a rewriting of the underlying code of the universe. We can actually observe the ghostly fingerprints of these collisions around a rapidly spinning black hole. A phenomenon known as frame dragging occurs. The black hole's immense rotation does not just pull on matter, it pulls on spacetime itself, twisting the entire region around it like thick honey being stirred. These are the engines that drive the universe's most exotic phenomena. The violent mergers of black holes, detected through the gravitational waves they send rippling across the cosmos, are direct evidence of spacetime being shaken to its core. It is within these incredible crucibles of gravity and motion that the theoretical seeds of chronotunnels could be sown. To witness these ideas in their most extreme form, we must look to the ultimate natural laboratories, the places where the normal rules break down completely. We must look into the abyss of a black hole. At the event horizon of a black hole, the universe performs a strange magic trick. From our perspective, watching from a safe distance, time for an object falling toward that boundary seems to slow to a complete stop. It fades from view, frozen forever on the edge. Yet for the object itself, the fall continues relentlessly, a one-way journey toward the crushing singularity at the center. This bizarre split in reality is a direct result of gravity warping time itself, a phenomenon predicted by Einstein. Then Stephen Hawking added a quantum twist. He showed that the empty space just outside the event horizon is not truly empty. It is a seething sea of virtual particles popping in and out of existence. Occasionally, a particle pair will form right at the brink, with one particle falling into the black hole and the other escaping into space. This escaping stream is known as Hawking radiation, a faint glow that slowly bleeds energy and therefore mass from the black hole over eons. It is a tiny quantum whisper from the edge of the abyss, our only theoretical window into the black hole's interior. We are no longer just theorizing about these space-time warps. The Event Horizon Telescope collaboration has given us our first direct images of the monsters at the centers of the galaxy M87 and our own Milky Way. Those iconic dark shadows surrounded by a fiery ring are not the black holes themselves, but their silhouette against the backdrop of intensely heated matter in the accretion disk. The bright ring is light from that superheated gas, bent in a perfect circle by the black hole's incredible gravity. it is a stunning confirmation of how severely these objects twist the fabric of reality. For chronotunnels, the most tantalizing possibility lies within a specific type of black hole, a rotating Kerr black hole. The mathematics suggest that past the event horizon of such a spinning vortex, there could exist pathways known as closed time-like curves. These are theoretical loops in spacetime where an object could, in principle, travel on a path that brings it back to its own past. This is not a metaphor, it is a direct mathematical consequence of the equations describing this extreme environment. It is a potential natural chronotunnel woven into the heart of a cosmic giant. The violent processes around these black holes are also factories for stellar echoes. The chaotic, high-energy physics of the accretion disk, where matter is torn apart and heated to millions of degrees, and the powerful jets of plasma that shoot out from the poles, are constantly generating flashes and eruptions of light. As this light travels through the warped spacetime around the black hole, some of it may take longer paths, creating delayed afterimages or echoes of the original event. By studying these echoes, we are effectively listening for the reverberations of spacetime itself. These cosmic powerhouses are not just destroyers of stars, they are our most powerful laboratories, places where we can search for the faint signatures of temporal interference, for the whispers from the edge of reality. The cosmos has a soundtrack, and we have only just learned how to hear it. The first direct detection of gravitational waves by the LIGO and Virgo observatories was not just a discovery, it was the opening of a new sense for humanity. We are no longer merely watching the silent movie of the universe, we are now listening to its symphony. These ripples in the fabric of spacetime are generated by the most violent events imaginable, the mergers of black holes and the collisions of neutron stars. When such colossal masses spiral together and crash, they shake the very foundations of reality, sending out waves that travel at the speed of light, stretching and squeezing everything in their path. Each signal is a unique cosmic fingerprint. By reading the subtle changes in the wave's frequency and amplitude, scientists can decode the story of the event that created it, learning the masses of the objects involved, how fast they were spinning, and how far away the cataclysm occurred. But the journey of these waves is as important as their origin. As a gravitational wave travels across the cosmos, it does not move through empty, uniform space. It passes through a landscape of varying gravity, past galaxies and dark matter halos. Just like light, these spacetime ripples can be gravitationally lensed. A massive object can bend the wave's path, potentially splitting it and creating multiple copies of the same signal that arrive at different times. This creates a gravitational echo, a faint replay of a cosmic crash. It is a delay that holds incredible information. By studying these echoes, we could map the invisible distribution of dark matter that warps the wave's journey, revealing the hidden skeleton of the cosmos. Our ability to listen is about to become vastly more powerful. Ground-based detectors like LIGO are sensitive to the high-frequency waves from stellar mass collisions. But future space-based observatories, like the planned Laser Interferometer Space Antenna, or LISA, will open up a whole new low-frequency band. This is the realm of supermassive black holes, monsters millions of times heavier than our Sun, orbiting each other in the hearts of galaxies. The waves from their mergers will be complex, lasting for years, and their interference patterns could be incredibly rich. It is within this intricate data that we might find our first clues of something even stranger. If a gravitational wave passes near a chronotunnel or another exotic spacetime structure, its signal could be distorted in ways that defy conventional explanation. The wave might carry a faint, anomalous echo, a signature of having traveled through a region where time itself is knotted. We are learning to listen to the vibrations of spacetime, and in their most subtle harmonies, we might just hear the whisper of a bridge to another time. Einstein called it spooky action at a distance, a phrase that perfectly captures the deep unease this quantum phenomenon stirs. Quantum entanglement challenges the very heart of our classical reality, where two particles can be created together and remain mysteriously linked, no matter how far apart they travel in space. Measure the spin or polarization of one particle, and the state of its partner is instantly determined. This connection appears to happen faster than light, seemingly ignoring the vast emptiness between them. It is as if the universe possesses a hidden, instantaneous communication channel, a notion that troubled Einstein because it defied the cosmic speed limit he had helped to establish. But what if this spooky action is not a violation of the rules, but a clue to a deeper layer of reality, one where space itself is an illusion? Some of the most forward-thinking theoretical physicists have proposed a radical answer, known as the ER=EPR Conjecture. This idea suggests that two entangled particles are not actually separate entities sending signals to each other. Instead, they are connected by a microscopic wormhole, a tiny chronotunnel woven into the fabric of spacetime itself. In this view, the eerie link between the particles is not a message traveling across a great distance, but a geometric connection, a shortcut through the hidden folds of the universe. The quantum information shared between them is literally threaded through this incredibly small bridge. This revolutionary idea implies that the fabric of quantum information and the geometry of spacetime are not just related, they are two sides of the same cosmic coin. The strange rules governing the quantum world might actually be dictating the very shape of reality. Experiments have consistently confirmed this non-local connection, with particles remaining entangled over distances of hundreds of kilometers. Each successful test pushes the boundaries of what we consider possible, forcing us to reconsider our most basic assumptions about communication and even causality, the law of cause and effect. If entanglement truly involves these microscopic chronotunnels, the implications for our story become staggering. It could provide a tangible mechanism for how stellar echoes operate. The light or gravitational waves from a long-dead star carrying its ancient information might not just be traveling a straight line through empty space. That information could be navigating a complex quantum-entangled network of microscopic bridges, creating the delayed and duplicated signals we observe. The quantum world is whispering that our cosmos is fundamentally interconnected, a single, unified whole where the stark separation between past and future may be nothing more than a persistent and convincing illusion. Our own experience of time as a relentless, forward-flowing river may be the universe's most convincing illusion. From a purely physical perspective, the nature of time stands as one of science's deepest enigmas. The block universe theory, supported by Einstein's relativity, presents a staggering picture. In this view, the past, present, and future are not successive states. They all exist simultaneously, laid out in a single, four-dimensional structure. What you perceive as the fleeting moment of now is merely your conscious awareness moving along a single thread through this eternal, unchanging block. This explains why the laws of physics work perfectly well in reverse, yet our everyday reality feels so different. That feeling of a one-way street, the arrow of time, is given to us by the second law of thermodynamics. This law describes the inevitable and universal tendency toward disorder, or entropy. A shattered glass does not reassemble itself, and a hot cup of coffee cools to room temperature, never spontaneously reheating. This constant increase in disorder provides the direction we call the future. But at the most fundamental level, the realm of quantum gravity where chronotunnels might exist, time itself may lose all meaning. Physicists like Carlo Rovelli propose that time is not a fundamental ingredient of reality. Instead, it is an emergent property, a macroscopic approximation that arises from the quantum interactions of countless particles, much like the concept of temperature emerges from the frantic motion of atoms. There is no single master clock for the universe, only a web of relative events. This radical perspective completely reframes our cosmic phenomena. Chronotunnels and stellar echoes would not be tunnels through time, but descriptions of how our conscious experience navigates a timeless reality. They would be pathways allowing information from different, eternally existing slices of the block universe to interact. A stellar echo would not be a message from the past, but a glimpse of another part of the static cosmic structure, made visible through the lens of warped space. This view forces a profound reconsideration of causality. If the future is already out there, written into the fabric of the cosmos, then what does it mean to travel to the past? Could you truly change an event that is as fixed and real as a point on a map? The logical paradoxes of time travel might dissolve if we accept that our journey would simply be a movement through a landscape where every moment is forever present. As we deconstruct the very idea of time, we must then ask what carries reality's structure across this timeless expanse. The answer lies in the universe's most faithful messengers, the entities that bind the block universe together, light and information. Light is the universe's oldest storyteller, carrying whispers from the deep passed directly to our eyes. We see the Andromeda galaxy not as a contemporary neighbor, but as it existed 2.5 million years ago, its ancient light a perfect stellar echo. This is not a theoretical abstraction, it is a direct observation of history written in photons. But light is not the only messenger on this cosmic journey. Ghostly neutrinos, nearly massless particles that pass through entire planets as if they were empty space, bring us news from the hearts of collapsing stars. High-energy cosmic rays, atomic nuclei accelerated to nearly the speed of light, carry their own coded tales of immense power. Each of these messengers travels across the cosmos, and their journeys are not straight lines. They are bent and delayed by the gravitational fields of every galaxy, every dark matter halo, and every invisible structure they pass. These distortions are not just noise, they are a treasure map. By carefully analyzing how the signal from a quasar is warped, or why a neutrino arrives with unexpected energy, we can infer the presence of hidden mass or even stranger things. The information they carry is our only tangible connection to events that occurred before our world was even formed. In the context of chronotunnels, this opens a breathtaking possibility. What if information itself could take a shortcut? A pulse of light or a stream of particles might not just travel through space, but through a temporary bridge in spacetime itself. To our telescopes and detectors, this could manifest as an anomalous signal, an echo that arrives too early or from the wrong direction, a piece of data that simply does not fit our standard models of the cosmos. It would be a message that seemingly broke the rules because it took a different kind of road. Hunting for these subtle fingerprints requires technology of almost unimaginable sensitivity. Observatories like the Ice Cube detector, buried deep in the Antarctic ice to catch rare neutrino interactions, or the Pierre Auger Observatory, which scans the sky for the highest energy cosmic rays, are our nets cast into the cosmic ocean. They are designed to catch these rare messengers and read their stories. As our instruments grow more advanced, we are not just building better telescopes, we are crafting finer keys to unlock the deeper secrets of reality, searching for the faint, encoded signature of time and space colliding. Our hunt for these cosmic ghosts demands tools that border on magic. We are building instruments of almost impossible sensitivity, machines designed to listen for the faintest whispers from the edge of reality. The James Webb Space Telescope acts as a perfect time machine, its infrared gaze piercing through cosmic dust to see the light from the first stars and galaxies. It is not just looking at ancient objects, it is actively collecting the oldest stellar echoes in the universe, the direct afterglow of creation itself. Each faint, redshifted photon is a piece of a puzzle from a time when reality was new. To feel the vibrations of spacetime, we are launching a new generation of gravitational wave observatories. The Laser Interferometer Space Antenna, or LISA, will be a fleet of 3 spacecraft flying in a vast triangle millions of kilometers across. It will sense the low-frequency hum of supermassive black holes merging, a cosmic chorus that ground-based detectors cannot hear. Within the complex waveforms of these collisions, scientists will search for subtle distortions, tiny hiccups in the signal that could indicate the waves passed through a region of knotted spacetime, a potential chronotunnel. On Earth, projects like the Vera C. Rubin Observatory will photograph the entire visible sky every few nights, creating a colossal movie of the cosmos. This relentless monitoring will catch countless fleeting events, supernova and stellar flares. By analyzing the precise curve of their brightening and fading, astronomers can search for anomalies, for a telltale double peak, or an unexpected delay that betrays the presence of a hidden echo. The quest moves into the quantum realm. The most precise atomic clocks ever built are now so sensitive they can measure the minuscule warping of time caused by a centimeter change in elevation, a direct test of general relativity on a tabletop. These clocks could, one day, detect the fleeting passage of a microscopic spacetime tunnel. Meanwhile, quantum computers might simulate the intense gravity around a black hole, allowing us to experiment with the physics of chronotunnels in a virtual environment. These are not separate projects, but a unified front in a grand scientific campaign. Each new instrument gives us a different sense with which to perceive the cosmos, a new way to cross-check a strange signal. A flicker of light seen by Webb, a distorted ripple detected by LISA, and an anomalous particle reading from a quantum sensor. Together they could form the first undeniable proof that our universe is woven through with bridges to other times. We are building the keys to unlock a deeper layer of reality. History's astronomical records are littered with stubborn anomalies that refuse to fit our tidy models. Among these cosmic outliers, we find our most compelling candidates for the collision of time and space. One such event was a brief, incredibly intense flash of gamma rays detected years ago. It appeared, shone with the power of 1 trillion suns, and then vanished without any trace of the lingering afterglow that always follows a supernova or star merger. For a moment, it was as if a door opened onto a region of pure energy and then slammed shut. Some theorists have playfully labeled it the Alcubierre white hole candidate, a potential transient chronotunnel briefly connecting to a region of the universe where time itself flows backward. Then there are the enigmatic fast radio bursts, or FRBs. These are millisecond-long blasts of radio waves from deep space, and while many are one-off events, some repeat in strange, complex patterns. A few of these repeating signals exhibit timing that is difficult to reconcile with a simple spinning neutron star. Instead, their intricate rhythm could be the signature of their light being gravitationally lensed through a complex knot of spacetime, a natural amplifier and delayer creating a stellar echo on an interstellar scale. On the grandest stage, we find the puzzling case of redshift quantization. When we measure the light from distant galaxies, we expect their redshifts, which indicate their speed and distance, to form a smooth, continuous distribution. Yet some studies suggest galaxies seem to cluster at specific redshift values, as if the universe were built on a giant, invisible lattice. This could be a statistical fluke, or it might be a ghostly imprint of the underlying topology of spacetime itself, a large-scale structure that funnels and organizes cosmic expansion. Perhaps the most famous anomaly is the cold spot in the cosmic microwave background, the ancient afterglow of the Big Bang. This vast region of space is unexpectedly colder than its surroundings. While most explanations involve vast cosmic voids, some have proposed a more radical idea that this blemish is a bruise from a collision with a parallel universe bubble, a catastrophic form of spacetime interaction that left a permanent scar on our own. These are not failures of our science, they are its lifeblood. Each unexplained signal, each statistical oddity, is a crack in the facade of our understanding, a place where a deeper truth might be shining through. To move from speculation to explanation, we must leave the telescope and turn to the pure language of the cosmos itself, the mathematics that describes how such wonders could be possible. The equations of general relativity do not forbid the existence of bridges through time. They provide the very blueprint. Deep within the mathematical landscape of Einstein's theory lies a solution known as the Morris-Thorne traversable wormhole, a precise recipe for a chronotunnel. This is not a vague idea, it is a specific geometric shape, a kind of cosmic throat connecting two distant regions of spacetime. The equations describe how this throat must be shaped, how it would bend the paths of light and matter, and most critically, how it would warp the flow of time for anything passing through. To visualize this, picture a simple sheet of paper representing space. A wormhole is not a tunnel drilled through the paper. It is more like folding the paper so two distant points touch, creating a shortcut. The mathematics defines the properties of that point of contact, the throat. But this elegant geometry comes with a profound catch. For this tunnel to remain open and stable, for it not to instantly collapse into a black hole the moment anything tries to enter, the equations demand the presence of a truly bizarre substance. It requires exotic matter, a theoretical form of energy that possesses negative energy density. This is not antimatter, which still has positive energy. This is something far stranger, something that pushes against gravity itself, propping the throat of the wormhole open like a cosmic pillar. The search for this exotic matter leads us directly to the frontier of quantum physics, where the vacuum of empty space is not truly empty. According to quantum field theory, so-called virtual particles are constantly flickering in and out of existence, and under certain conditions, this can create regions of negative energy. The Casimir effect, where two metal plates placed extremely close together in a vacuum experience a slight attractive force, is a real-world demonstration of this negative energy at a microscopic scale. But to stabilize a chronotunnel large enough for even a single particle to pass, we would need to harness this effect on a titanic scale, a challenge that currently lies far beyond our capabilities. To understand how such a structure might form naturally, physicists turn to immense supercomputers. They run simulations of colliding black holes, modeling the incredible turbulence in the fabric of spacetime that such an event creates. Within these numerical storms, they search for any sign that the violent warping could, even for a fleeting instant, twist reality into the specific shape described by the wormhole equations. These models are far from abstract games. They make concrete, testable predictions. A real chronotunnel would leave a distinct fingerprint on any light passing near it. It would create a unique pattern of gravitational lensing, perhaps producing multiple, distorted images of a single background star. It might emit a specific signature of Hawking radiation, or cause a strange, localized shift in the flow of time that could, in theory, be detected by a network of ultra-precise atomic clocks. The mathematics paints a stunning picture of a connected cosmos, but it also presents us with a monumental question. If such bridges are possible, what incredible substance could possibly hold them open against the crushing weight of the entire universe? The exotic matter needed to prop open a chronotunnel defies everything we know about substance. This is not a new element for the periodic table, but a form of energy with a truly bizarre property: negative energy density. Think of it as a kind of cosmic anti-gravity, where normal matter and energy create an attractive pull, warping space inward. This exotic substance would generate a repulsive push, forcing the throat of a wormhole to remain open against its own natural tendency to crush shut. Without this negative pressure, any passage through time and space would instantly collapse into a singularity the moment it formed. We are not completely in the dark about such strange physics. Quantum field theory gives us a tiny glimpse in a laboratory phenomenon called the Casimir effect. When two perfectly smooth metal plates are placed incredibly close together in a vacuum, they experience a faint, mysterious force pulling them together. This happens because the space between the plates actually has a lower energy density than the empty space outside, creating a minute region of negative energy. It is a real, measurable whisper of the exact effect we would need, but the scale of the challenge is almost incomprehensible. To stabilize a chronotunnel just 1 meter wide, the calculations suggest you would need to concentrate negative energy equivalent to the mass of Jupiter. To make it traversable for a human, the energy requirement might approach the Planck scale, the absolute upper limit where the known laws of physics completely break down. This is not an engineering problem, it is a fundamental barrier in our understanding of reality. This immense need for power forces us to look at the cosmos itself for a solution. Could the mysterious dark energy, which is relentlessly accelerating the expansion of the entire universe, be a natural form of this exotic substance? Its repulsive gravity is exactly the kind of effect we would need, but harnessing a force that dominates the entire cosmos is a fantasy far beyond our current reach. Our best hope for understanding may lie in smashing matter apart. High-energy particle colliders like the Large Hadron Collider are, in a way, exotic matter factories. By recreating the conditions of the early universe, they probe the fundamental quantum fields from which all particles and forces emerge. It is within these violent, microscopic collisions that we might one day observe a transient state with the right negative energy properties, even if only for a fraction of a second. Until we can either generate or find a cosmic source of this repulsive stuff, traversable chronotunnels will remain locked in the elegant prison of mathematics. Yet this very limitation points our gaze toward the only places in the universe with energy enough to possibly bend the rules, the crucibles where space and time are born and torn apart. Deep within the frozen architecture of the cosmos may lie cracks from its very formation. These are cosmic strings, not made of any ordinary material, but one-dimensional defects in the fabric of spacetime itself. They are thought to be relics of the universe's violent infancy, formed during a phase transition as the cosmos cooled, much like cracks appearing in ice as water freezes. The properties of these entities are almost beyond belief. A cosmic string could be thinner than a single proton, yet each centimeter of its infinite length might contain the mass of an entire mountain range. This incredible density warps the space around it in a unique way. Instead of creating a deep well of gravity like a planet or a star, a cosmic string pulls spacetime into a conical shape. Picture a piece of paper. If you remove a single, thin slice from it and then tape the edges back together, the paper now forms a cone. Walking a full circle around the apex of that cone does not bring you back to your exact starting point. This is the geometry around a cosmic string. It acts as a powerful and perfect gravitational lens. Light from a single galaxy directly behind the string would be split into two perfect, identical images on either side of this cosmic filament, a ghostly double vision written into the sky. The true potential for chronotunnels emerges when these strings interact. If two cosmic strings were to move past each other at high speed, their combined, swirling gravitational fields could twist spacetime into such a complex knot that it might theoretically form a closed time-like curve. This is a path through spacetime that loops back onto itself, a natural chronotunnel spun from the dance of these primordial defects. While we have not yet confirmed their existence, we are searching for their fingerprints. The immense energy of a snapping cosmic string would send powerful bursts of gravitational waves rippling across the universe, a signature that new observatories are poised to detect. They could also have left faint, linear scratches in the pattern of the cosmic microwave background. These strings are not merely isolated curiosities. They are threads that may have woven the largest structure we know, the cosmic web itself. This vast cosmic architecture began as the faintest whisper. The entire universe we see today, with its glittering galaxies and immense voids, grew from microscopic quantum fluctuations in the first moments after the Big Bang. These tiny ripples in the density of the primordial cosmos were stretched to astronomical sizes by a brief but incredible period of inflation, seeding the gravitational blueprint for everything to come. Gravity then spent billions of years sculpting those seeds into the universe's dominant structure, a magnificent cosmic web. Picture a colossal spiderweb spun across the darkness, its silken threads stretching for hundreds of millions of light years. The bright, glowing knots where the threads intersect are massive galaxy clusters, home to thousands of galaxies. The long, faint filaments connecting them are traced by streams of galaxies and an immense amount of dark matter. And between the threads lie the vast, empty cosmic voids, deserts of near-nothingness that span incomprehensible distances. This is not a static sculpture. It is a dynamic, flowing river of matter and energy, with galaxies steadily migrating along the filaments toward the dense clusters, drawn in by their immense gravitational pull. The sheer scale of this web means its gravity does not just pull on galaxies, it warps the very space it occupies. The gravitational potential of a massive filament or a cluster acts as a lens, bending the light from objects far behind it. This weak gravitational lensing creates a complex tapestry of subtle distortions, stretching and magnifying the images of distant galaxies into faint, ethereal arcs. It is within these deep gravitational wells that the collision of time and space becomes tangible. At the heart of a massive galaxy cluster, gravity is so intense that time itself is measurably slowed. A clock placed there would tick more slowly than one out in the emptiness of a void. This is not a theoretical idea, it is a real effect predicted by general relativity and confirmed by observations. Light traveling through this warped landscape does not take a single, straight path. From a single background quasar, its light can be split, taking multiple routes around the cluster. Each path is a different journey through the hills and valleys of spacetime, and each one takes a different amount of time to reach us. We see the same quasar at multiple points in its history simultaneously, a stellar echo orchestrated by the largest structures in existence. This leads to a profound speculation. Could the topology of the cosmic web itself be more complex than we realize? If the large-scale geometry of spacetime contains non-trivial structures, like handles or bridges connecting distant filaments, these could theoretically function as large-scale chronotunnels. They would not be tunnels built by an advanced civilization, but natural features of the universe's architecture, woven into its very fabric during its birth. To test these ideas, we must map the invisible. Projects like the Dark Energy Survey meticulously chart the distortions caused by weak gravitational lensing across vast swaths of the sky. By analyzing how the light from millions of galaxies is subtly bent, they can trace the underlying distribution of dark matter, revealing the hidden skeleton of the cosmic web. This is how we understand the geometry of spacetime on the grandest scales. This immense, interconnected architecture does more than just house galaxies. It sets the stage for the universe's most violent performances. Within the dense nodes of this web, where gravity reigns supreme, the conditions are perfect for the ultimate collisions of time and space. These cosmic explosions are the universe's final shout. A gamma-ray burst, or GRB, represents the most powerful known cataclysm, a fleeting scream of energy that outshines entire galaxies. In just a few seconds, one of these events can release more power than our Sun will emit across its entire 10 billion-year lifespan. They are likely born from the death throes of the most massive stars, collapsing into black holes, or from the violent, final embrace of two neutron stars. The light they produce is not a simple flash. It is a symphony of chaos, a light curve of rapid, intense flares followed by a lingering afterglow that can shine across the electromagnetic spectrum for days or even weeks. It is within this intricate fingerprint of light that we might find our most compelling clues. Some of these bursts exhibit strange precursor flares, bright flashes that occur moments before the main event, or they show repeating, rhythmic patterns in their high-energy emission. One possible explanation is that we are witnessing a stellar echo on a truly colossal scale. The initial blast of gamma rays might be gravitationally lensed by an invisible object between us and the burst, perhaps a dark matter halo or even a dense knot of spacetime itself. This lens could split the light, sending one pulse directly to us while bending another on a longer path, creating that eerie, delayed repetition. The sheer energy and short duration of these bursts make them perfect for an even more profound test. As the gamma-ray photons race across billions of light-years, they are sensitive to the very texture of the cosmos. Some theories of quantum gravity suggest that spacetime is not perfectly smooth, but has a fine, granular structure like the pixels on a screen. Over such immense distances, these tiny imperfections could subtly alter the energy of the highest energy photons, or cause a minute delay between their arrival times compared to lower energy light. A gamma-ray burst is therefore a natural experiment, sending a clean, powerful signal through the quantum foam of the universe for us to decode. Now, consider what would happen if one of these titanic explosions occurred in the vicinity of a chronotunnel. The resulting flash would not travel a single path. It would be funneled, split, and scrambled by the exotic geometry of the tunnel itself. We might observe multiple, identical bursts from the same point in the sky, separated by hours or days, each one a ghostly replay of the original cataclysm. Or we might see a single burst with an impossibly complex internal structure, its light having been folded and refolded through a spacetime shortcut. These are the observational signatures that astronomers actively hunt for within the torrents of data. The aftermath of such an explosion is just as telling. The collapsing star or merging neutron stars often leave behind a newborn black hole or a rapidly spinning magnetar, a neutron star with an unimaginably powerful magnetic field. These remnants become new anchors of extreme gravity, warping their local spacetime and continuing to produce energetic emissions. They are the cradles where future chronotunnels might one day form, the next generation of cosmic bridges born from the ashes of the old. In the violent death of a star, we find a fleeting window into the deepest laws of physics, a place where time and space are torn apart and stitched back together. The violent dance of two neutron stars is a forge where the universe creates its rarest treasures. When these unimaginably dense corpses spiral together and collide, they do more than shake the fabric of spacetime. They seed the cosmos with the very elements that make worlds like ours possible. The event known as GW170817 was our first direct glimpse into this alchemy. For the first time in history, we felt the gravitational waves from the merger ripple through our detectors, and then, just moments later, saw the brilliant flash of light across every telescope we could point at it. That light was a kilonova, a thermal explosion powered by the radioactive decay of heavy elements freshly forged in the cosmic fire. In that single event, we witnessed the birth of gold, platinum, and other precious metals, proving that the jewelry on your finger was likely born in a cataclysm more powerful than a billion suns. But the scientific value runs even deeper. For a few fleeting moments during the collision, matter is compressed to densities so extreme that protons and neutrons dissolve into a soup of their constituent quarks. This quark-gluon plasma is a state of matter not seen since the first microsecond after the Big Bang, a place where the strong nuclear force and gravity meet in a violent embrace. It is a natural laboratory for physics we cannot hope to recreate on Earth. The aftermath of the merger holds its own mysteries. The gravitational wave signal did not simply stop at the moment of impact. Scientists carefully sifted through the data, listening for faint echoes in the ringing of spacetime itself. Such a signal could be the signature of a hypermassive neutron star, a single object so dense and unstable that it pulses and vibrates before finally collapsing into a black hole. Or, more speculatively, those echoes could hint at something even stranger, a newborn black hole whose event horizon is not quite what our textbooks predict, a transient doorway where the normal rules are temporarily suspended. This is where stellar echoes are born in their most extreme form, the incredible energy released in the merger and the subsequent formation of a new black hole or magnetar sends powerful flashes of light and gravitational ripples out into the cosmos. As these signals travel through the severely warped spacetime left behind by the collision, some are delayed, some are bent, creating a complex series of afterimages and reverberations. We are effectively listening to the echo of spacetime rearranging itself. The gold forged in that explosion is then blasted out into the galaxy, eventually finding its way into clouds of gas and dust that will one day coalesce into new stars and planets. It is a humbling thought that the very atoms that make up our world were once part of such a violent, beautiful, and fundamental cosmic process. That invisible hand sculpting the cosmos is the ghost in the machine, dark matter. It makes up over a quarter of everything in the universe, yet it refuses to interact with light in any way. We cannot see it, touch it, or contain it. We only know it is there because of its immense gravitational pull, a force strong enough to hold entire galaxies together and weave the vast filaments of the cosmic web. Without this unseen scaffolding, stars would fly apart and the universe would look nothing like it does today. The true identity of dark matter is one of physics' greatest mysteries. What is it made of? The leading candidates are theoretical particles with names that sound like they are from science fiction. Weakly interacting massive particles, or WIMP, are heavy entities that barely interact with normal matter. Actions are another possibility, incredibly light particles that might flow through the cosmos like a ghostly wind. But there is a more exotic idea that dark matter could be made of primordial black holes, ancient relics formed in the first chaotic moments after the Big Bang. If that were true, these black holes would be perfect gravitational lenses. A primordial black hole drifting between us and a distant star would warp the starlight, causing the star to temporarily brighten in a specific, telltale way, a stellar echo created by an invisible, wandering mass. This gravitational footprint is the key to dark matter's profound connection to our story of time and space. Every galaxy is embedded within a massive, diffuse halo of this mysterious substance. This halo creates a deep well of gravity, a landscape of hills and valleys in spacetime that every ray of light must traverse. The distribution of dark matter literally sets the stage for the lensing effects that create stellar echoes, determining how the past is reflected and delayed for us to observe. Some speculative theories suggest dark matter might not be completely inert. It could have its own hidden forces, a shadow physics governing interactions within its own realm. If so, dark matter could clump into structures even denser than we predict, forming knots of intense gravity that could warp local spacetime in strange and unexpected ways. These dense cores could act as anchors or focal points, regions where the fabric of reality is stressed enough that a chronotunnel might be more likely to form or remain stable. The invisible architecture of dark matter does not just host the cosmic dance of time and space, it may actively choreograph it. To build a stable bridge across time, you would need to overcome the universe's natural tendency to collapse such a structure. The immense gravitational potential provided by a dense concentration of dark matter could, in theory, provide the foundational support, the cosmic bedrock, upon which the delicate geometry of a chronotunnel could be built. Its elusive nature is what makes it so compelling, for in mapping its shadow, we might finally trace the contours of reality's deepest secrets. Our universe may not be a solitary island in the void, but one page in an infinite cosmic library. This is the Multiverse Hypothesis, a staggering idea that what we call reality is just one possibility in a vast ensemble of universes, each with its own unique laws and constants. Some might have stronger gravity, others might have no light at all. The mechanism for this cosmic proliferation is built right into our best models of the beginning. The theory of eternal inflation suggests that the rapid expansion of the early universe never truly stopped everywhere. Instead, our entire cosmos might be a single bubble that formed in a still inflating meta-universe, with countless other bubbles constantly budding off into their own separate realities, forever disconnected from our own. The walls of these bubbles are not solid, they are domains of incredibly high energy. If two of these budding universes were to collide, the impact would be a cosmological event of unimaginable scale. Such a collision would not be a silent touch. It could leave a distinct bruise on the cosmic microwave background, a strange circular pattern of hot or cold spots, or it might even create a localized region of space where the fundamental laws of physics are subtly different from everywhere else. A more intricate version of this idea emerges from string theory. This framework suggests that the specific properties of our universe are determined by how tiny, curled up extra dimensions are shaped. The number of possible shapes is astronomically large, perhaps infinite, with each one corresponding to a different vacuum state, and thus a different universe with its own physics. This is the string theory landscape, a theoretical terrain of countless possible worlds. This framework forces a radical reinterpretation of our core phenomena. If chronotunnels do exist, their potential might be even greater than connecting different times. They could, in principle, be bridges not just through time, but across the void to other universes entirely. A stable tunnel might not open onto the Jurassic period, but onto a reality where stars never formed. While this remains one of the most speculative ideas in physics, it offers a new lens for understanding anomalies. What if a stellar echo is not just a delayed signal from our own past? That strange, repeating fast radio burst with its inexplicable pattern could be interpreted as interference, a form of cosmic crosstalk where the light from a star in a neighboring universe is briefly leaking into our own through a temporary flaw in the fabric between worlds. The multiverse hypothesis, by its very nature, pushes against the limits of the scientific method. How can we test something that is, by definition, beyond our observational reach? For now, it remains a powerful theoretical tool, a concept that stretches our imagination and forces us to confront the deepest questions. What is the ultimate nature of reality? Is our universe fine-tuned for life by chance, or is it simply one of countless experiments in a much grander cosmic tapestry? The logical knots of time travel are as unavoidable as they are fascinating. The classic grandfather paradox presents a stark contradiction. If you were to travel back and prevent your own grandfather from meeting your grandmother, you would erase the very conditions of your own existence, making the journey impossible in the first place. This is not just a plot hole for science fiction, it is a direct challenge to the logical consistency of reality. How can the universe resolve such a loop? One compelling answer comes from the Novikov self-consistency principle. This idea asserts that the flow of history is a single, unchangeable thread. Any actions a time traveler attempts in the past were always a part of that timeline. You might intend to change history, but your very presence and every move you make would be seamlessly woven into the events that always happened. You could not create a paradox because the universe simply would not allow it. Your attempt to interfere would, through a complex and inevitable chain of coincidences, end up causing the very event you sought to prevent. In this view, free will becomes an illusion within the closed loop of time, and destiny is a story that has already been fully written. There is another, perhaps even stranger, way out of the paradox. The many worlds interpretation of quantum mechanics suggests that every quantum decision spawns a new, branching universe. Under this model, traveling to the past would not send you into your own history, but would instead create a fork in the road. The moment you arrive, a new timeline branches off from the original. In this new reality, you could change anything you want, save your grandfather or not, and it would have no effect on the timeline you left behind. Your original history remains untouched, a parallel stream flowing beside the one you now inhabit. This solves the logical paradox but introduces an existential dizziness. It implies a multiverse of infinite alternatives, where every possible past and every conceivable future is real somewhere. These ideas force us to re-examine the stellar echoes we have been discussing. If we are receiving information from the deep past, are we simply observing a fixed, fossilized record? Or could our act of observation in the present somehow influence that past signal? This touches on the quantum concept of retrocausality, where an effect can precede its cause. While highly speculative, it hints at a universe where the arrow of time is not a rigid one-way street, but a two-way dialogue. These are not merely abstract games for physicists. Causality, the simple idea that a cause must come before its effect, is the bedrock of science and our daily lives. It allows us to learn from the past and plan for the future. If chronotunnels or retrocausal echoes were proven real, that foundation would shake. Our understanding of history would transform from a fixed narrative into something more fluid, a story that might still be in conversation with the present. The implications would ripple through every aspect of human knowledge, from the laws we uphold to the very stories we tell about who we are and how we came to be. The clocks on the satellites guiding your car's navigation are wrong, and they are wrong by design. Each atomic clock aboard a global positioning system satellite ticks 38 millionths of a second faster every single day than its identical counterpart on the ground. This is not a manufacturing error, it is a direct and continuous confirmation of Einstein's theory of relativity. The satellite's high orbital speed causes a special relativistic slowdown of time, while its position in Earth's weaker gravity field causes a general relativistic speedup. The net effect is that time itself runs faster up there, and if the system's engineers did not deliberately correct for this drift, your GPS would accumulate errors of several kilometers within just a few hours. This is time dilation in action, a fundamental feature of our universe that we must account for to see the cosmos clearly. This relativistic lens profoundly distorts our view of the most violent events in space. When astronomers observe a supernova in a galaxy billions of light-years away, they witness the explosion in slow motion. The light curve, the graph of how the supernova brightens and fades, appears stretched out over a longer period compared to a nearby supernova. This is because the expansion of the universe has stretched space itself, which in turn stretches the passage of time for the light traveling through it. We are not just seeing the event as it was in the past, we are seeing it unfold at a slower rate. By measuring this temporal stretching across vast cosmic distances, scientists can trace the history of the universe's expansion, providing crucial data to understand the mysterious dark energy that is pushing galaxies apart. The most extreme time warps occur in the gravitational grip of dense stellar remnants. On the surface of a white dwarf or a neutron star, gravity is so intense that time crawls compared to the rest of the universe. A single process, like the flicker of a flare on the star's surface, would appear to a distant observer like us to unfold in a drawn-out, sluggish manner. The clocks there are literally running slow, a phenomenon we can detect in the precise timing of pulses from rotating neutron stars. This is not an illusion, it is the physical reality of a malleable spacetime. Our ability to measure and understand these effects is what grounds the more speculative ideas of chronotunnels in established science. If gravity can slow time to a crawl, then what might it do when twisted into a knot by a spinning black hole or a cosmic string? The same principles that guide our satellites and decode distant supernovae suggest that the universe holds far deeper temporal mysteries waiting to be unraveled. Our search for cosmic company has always been bound by the speed of light. For decades, the quest for extraterrestrial intelligence has scanned the skies for radio signals or laser pulses, assuming any message would be a straightforward broadcast traveling at light speed across the void. This entire paradigm could be fundamentally incomplete. If chronotunnels are possible, then a civilization far more advanced than our own would likely have mastered their use, not for physical travel, but for something far more practical, instantaneous communication across the galaxy. Imagine receiving a complex data stream that appears to originate from a point in empty space, with no star system nearby to host its source, or a signal that arrives before a corresponding stellar event, seemingly breaking the chain of cause and effect. Such a message would not be traveling through space, but around it, using a shortcut in spacetime itself. This would explain signals that defy conventional astronomical models, appearing to come from nowhere and repeating in patterns that natural astrophysics cannot easily replicate. The famous WOW signal, a powerful, narrowband radio burst detected in 1977, remains a perfect example. It was never heard again despite repeated searches. Could it have been a one-time data packet sent through a temporary spacetime bridge that subsequently collapsed? A single page of a message we could never fully receive. An even more deliberate form of communication might involve engineered stellar echoes. Instead of relying on natural gravitational lensing to create a delayed signal, an advanced species could artificially create one. They might place a powerful transmitter near a known gravitational lens, like a black hole or a dense dark matter knot, programming it to send pulses that would be lensed into a specific, complex rhythm. This repeating pattern, a precise echo in the light of a star, would be a clear beacon designed to stand out against the random noise of the cosmos and catch the attention of a species just learning to listen. Our search is now expanding to look for these broader technosignatures. We are no longer just listening for a simple hello. We are searching for the architectural fingerprints of cosmic engineers, evidence of projects on a scale that manipulates the fabric of reality. The stable structure of a chronotunnel or a stellar echo with an impossibly perfect mathematical signature would be the ultimate discovery. It would not just tell us that we are not alone. It would reveal an intelligence so profound that it has learned to write its messages not on radio waves, but onto the canvas of space-time. Finding such a signature would forever shift our place in the universe, from lonely inhabitants of a single planet to students in a galactic classroom of ancient, star-faring civilizations. Why does the universe seem perfectly tailored for life? This profound puzzle is known as the Anthropic principle, the observation that the fundamental constants of nature, from the strength of gravity to the mass of an electron, are set with such incredible precision that even a tiny change would render the cosmos sterile and lifeless. It appears as though the universe won a cosmic lottery of almost impossible odds. One compelling answer lies within the multiverse idea, where our universe is just one bubble in a vast foam of realities, and we simply happen to inhabit the one where the numbers came out right. But chronotunnels offer a far more radical and intimate explanation. What if the universe is not just lucky, but logically self-consistent across all of time? This is the core of the participatory anthropic principle, a breathtaking idea that suggests observers in the future could reach back through temporal bridges and subtly influence the initial conditions of the Big Bang itself, ensuring the cosmic chain of events that leads to their own existence. In this view, the universe literally bootstraps itself into being, a closed loop of cause and effect where the final result helps create its own beginning. The stellar echoes we detect, those ghostly repeats of ancient starlight, might be more than just cosmic reflections. They could be the faint, residual tremors of this bootstrap process, the lingering signature of information looping back through time to reinforce the stability of the timeline. While this remains one of the most speculative ideas in all of physics, it forges a direct link between the mystery of fine-tuning and the nature of time itself. It proposes that the life-friendly nature of our cosmos is not a random accident, but a fundamental consequence of a universe where past and future are in constant dialogue. This line of thinking inevitably blurs the boundary between hard physics and deep metaphysics, forcing us to confront the possibility that consciousness is not just a passive passenger in the cosmos, but may play an active, even necessary, role in the very structure of reality. As we stand here, conscious beings in a universe seemingly made for us, we are also peering into a future where the very act of observation might be the thread that holds all of existence together. Humanity's distant future may transform us from observers of spacetime into its architects. The theoretical blueprint for such power already exists in concepts like the Alcubierre warp drive. This is not a conventional engine burning fuel, but a proposed method of manipulating the fabric of reality itself. The idea involves creating a bubble of flat spacetime around a ship, while contracting the fabric in front of it and expanding the space behind. The ship itself would not move through space at all. It would be carried along as the spacetime around it flows, like a surfer riding a wave. This could effectively allow for faster-than-light travel without breaking the universal speed limit, because the vessel is stationary within its local bubble, while the universe itself shifts around it. The energy and material requirements for such a feat are currently beyond imagination, demanding the creation and control of exotic matter with negative energy density. To generate the necessary power, future civilizations might construct colossal structures like a Dyson sphere, a theoretical megastructure that encircles a star to capture nearly all of its energy output. Harnessing the total power of a sun could provide the means to stabilize a chronotunnel, not just for sending messages, but potentially for transportation. The ethical weight of such technology would be staggering. Creating a stable wormhole or a warp bubble is not like building a bridge. You are altering the fundamental geometry of the universe. A miscalculation could unleash gravitational tidal forces that rip planets apart or create unpredictable singularities. The very act of punching a hole through spacetime could have ripple effects that travel across light years with consequences we cannot possibly foresee. This is not just engineering, it is cosmic responsibility. The first tentative steps toward this future are not happening in massive shipyards, but in quiet laboratories. Scientists are already learning to control quantum states with incredible precision, simulating the effects of intense gravitational fields and probing the nature of vacuum energy. Each experiment, no matter how small, is a rehearsal for a future where we no longer just listen to the echoes of the cosmos, but learn to answer back. While these ideas dwell in the realm of speculative science, they chart a potential path for our species, a destiny where we step onto the stage and become active participants in the grand, unfolding drama of time and space. A starry dome above you is not just a ceiling, it is a portal. Inside planetariums and science museums across the world, immersive visualizations are now translating the mind-bending physics of chronotunnels into a visceral experience. You can float through the swirling throat of a simulated wormhole, watching as starlight twists into a ring of fire around you, or witness a distant quasar split into multiple, shimmering images by an invisible gravitational lens. These are not just spectacular shows, they are fundamental tools for education, transforming abstract mathematics into something you can feel in your bones. This same mission of translation drives documentaries and YouTube channels dedicated to space mysteries, where complex research is woven into compelling stories that capture the heart as well as the mind. They answer the most human of questions: what does this mean for us and why should we care? But the journey does not stop at watching, it extends to doing. Citizen science projects have thrown open the doors of cosmic discovery to everyone. From a home computer, you can now sift through telescope images, classifying the shapes of distant galaxies or hunting for the faint, telltale arcs of gravitational lensing. Your click could be the one that identifies a rare stellar echo or helps map the dark matter halo of a far-off cluster. You are not just learning about science, you are actively participating in it. In classrooms, these cosmic ideas become powerful engines for teaching critical thinking. A simple thought experiment about time travel, like the grandfather paradox, is not just a fun puzzle. It is a perfect gateway to discussing the scientific method. How would a physicist test such a fantastical idea? What evidence would we look for? This process shows that science is not a dusty collection of facts, but a dynamic, creative, and sometimes deeply strange endeavor to understand reality. By making these frontiers accessible, we demystify the entire scientific process. We reveal it as a shared human adventure, one that thrives on curiosity and is fueled by public wonder and support. The child who gazes up at a planetarium simulation of a spinning black hole today might be the scientist who deciphers its Hawking radiation tomorrow. Our collective engagement with these mysteries does more than just spread knowledge. It ensures that the fundamental research which drives all discovery continues to have a foundation of public understanding and enthusiasm. The questions we dare to ask together now will light the path for the breakthroughs of the future. the power to reshape time itself carries a responsibility we can scarcely comprehend. Manipulating the fabric of spacetime is not like any engineering project we have ever undertaken. The colossal energy required to stabilize a chronotunnel, if we could even harness it, might demand resources on a planetary scale, with environmental consequences that ripple across centuries. And what if a stabilized tunnel became unstable? A collapsing wormhole could unleash gravitational tides or unpredictable singularities, posing risks not just to our world, but to the integrity of the local cosmos. This is no longer just exploration, it is a form of cosmic architecture with existential stakes. The science fiction concept of a prime directive, a strict policy of non-interference, becomes a vital ethical framework. If we were to open a bridge to the past, the temptation to observe or even interact would be immense. But even passive observation, guided by the strange rules of quantum mechanics, could potentially influence the system being watched. By merely looking into the past, might we inadvertently change it? The ethical dilemmas extend to communication. Decoding a message from a long-dead civilization, a true stellar echo carrying the final words of a species, would be the greatest archaeological find in history. But should we answer, our reply, sent through the same cosmic lens, could reach them at a pivotal moment in their development, irrevocably altering their cultural and technological trajectory. We would become actors in a drama that for them is still unfolding. These questions demand that we establish protocols for responsible exploration now, long before the technology is within our grasp. We need international and perhaps one day intertemporal agreements on how to proceed with wisdom. The greatest challenge of our future may not be unlocking the secrets of chronotunnels, but learning how to wield that knowledge without breaking the universe we call home. Science fiction gave us our first glimpse of a chronotunnel long before the equations were widely understood. H.G. Wells' The Time Machine did not just tell a thrilling story. It planted a powerful idea in the cultural consciousness, the notion that time could be a landscape to be traversed. This is the essence of the warp drive effect, where a fictional concept captures the imagination of a future scientist, providing a creative spark that eventually fuels real-world research. The very terms we use to discuss these ideas, from wormholes to multiverses, were often popularized by novels and films, creating a shared language that makes the public more receptive to the complex science behind them. Authors like Arthur C. Clarke and Carl Sagan understood this power intimately. Clarke worked with physicists to ensure the orbital mechanics in 2001, A Space Odyssey, were plausible, while Sagan consulted with Kip Thorne to design a scientifically grounded wormhole for his novel Contact. This commitment to authenticity lent their stories a profound sense of possibility, making the incredible feel tangible. Science fiction serves as a vital sandbox for humanity. It allows us to conduct thought experiments on a grand scale, exploring not just the physics of a time machine, but the human consequences. What happens to society if the past becomes a tourist destination? How does personal identity change if you can meet your younger self? These narratives let us grapple with the ethical and philosophical ramifications of future discoveries in a safe, imaginative space, preparing our minds for the day the science might catch up. This creates a beautiful, virtuous cycle. A new theory in physics inspires a science fiction author to write a story. That story then inspires a new generation of students to become scientists, who then ask new questions that push the theory even further. This creative partnership is not a distraction from real science. It is a fundamental driver of our cultural and scientific evolution, constantly stretching the boundaries of what we dare to believe is possible. The two pillars of modern physics are at war with one another. General relativity paints the cosmos on a grand canvas where planets and stars glide through a smooth, curving spacetime. Quantum mechanics reveals a frantic, probabilistic microverse where particles pop in and out of existence and reality is fundamentally grainy. Uniting these two visions into a single theory of quantum gravity is the paramount challenge of our scientific age. This is not just an academic exercise, it is a quest to understand reality at its most fundamental level. The leading candidates for this unification, string theory and loop quantum gravity, offer radically different pictures of the cosmos. String theory proposes that the fundamental constituents of reality are not point particles, but tiny, vibrating strings. Their different vibrational modes give rise to all the particles and forces we observe. This framework often requires extra dimensions of space, curled up into shapes too small for us to perceive. In this view, a phenomenon like a chronotunnel could be a dynamic configuration of these strings and branes, a resonant vibration that temporarily stitches together distant regions of the multiverse. Loop quantum gravity takes a different path. It suggests that spacetime itself is not continuous, but is woven from a network of finite, discrete loops. Picture the fabric of reality as a chainmail tunic, with each interlocking ring representing a tiny, indivisible unit of space. In this model, the smooth geometry of general relativity is an approximation that emerges from this underlying quantum network, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. A chronotunnel, then, might be a specific knot or twist in this cosmic weave, a place where the loops connect in a way that creates a shortcut through the network. The conflict is profound. Relativity is deterministic, insisting that if you know the state of the universe now, you can calculate its entire future and past. Quantum mechanics is inherently probabilistic, dealing in possibilities and uncertainties. A theory of quantum gravity must resolve this clash, telling us whether the universe is ultimately predictable or ruled by chance. We are now designing experiments to probe this mysterious interface. Imagine placing a tiny, supercooled crystal in a state of quantum superposition, suspended between two possible locations, and then dropping it in a powerful gravitational field. Would gravity force it to choose a single path, breaking the quantum magic, or would the crystal remain in both places at once, demonstrating that gravity itself is quantum? Such delicate tests are becoming possible, and their results will guide us toward the correct theory. The ultimate reward for this grand unification is staggering. It would unravel the secrets of the Big Bang's first moment and reveal the true fate of matter inside a black hole. Most critically, it would provide a final, mathematical verdict on the physical possibility of chronotunnels. Are they a fleeting feature of the quantum foam, a stable structure in the cosmic architecture, or merely a beautiful mirage in the equations? The answer lies in the final chapter of this unification story, a chapter we are only just beginning to write. Our journey ends where it began, staring up at a starry sky that is no longer a silent, static picture. It is a living, breathing chronicle written in light and gravity, a story where time and space are not separate actors but partners in a single, magnificent dance. We have ventured from the crushing darkness of black holes to the seething quantum foam, discovering that chronotunnels and stellar echoes are not just science fiction. They are the natural consequences of a cosmos governed by relativity and quantum mechanics, clues pointing toward a deeper, unified reality. This exploration reveals a universe that is profoundly interconnected, a single block of spacetime where the past, present, and future might all exist simultaneously, forever linked by the information carried on light and gravitational waves. The implications ripple outward, touching the fine-tuning of the cosmos. the potential for communication across eons, and the ultimate future of intelligence itself. While countless mysteries remain, from the nature of dark matter to the final theory of quantum gravity, the pursuit itself is a testament to human curiosity. This is not an end, but an invitation for you to continue the adventure. Look up at the night sky and see it for what it truly is, a timeless tapestry still being woven. Share your own wonder and questions in the comments below, and join us as we keep unraveling the secrets of the cosmos. The final frontier is not just space, but the very nature of time, and our journey into its heart has only just begun.